Hi there. Seems like I'm recording. My name is Dr. A.J. Kumar, PhD, and today is Abstract Algebra 13, which is the setup and outline of a topic which I'm calling rulers and protractors. Maybe another way to call it would be rational trigonometry. And our two fundamental ideas are quadrance and spread, and these are replacements for length and angle. And they're better in the sense that they're computable and we can compute them exactly, and they're algebraic rather than these transcendental operations. And if they're algebraic, that means you can define them over an arbitrary field rather than just the rationals. So, some context. Talking about two dimensions here. Everything is rational. There's no reals. Reals are intervals. They are not numbers. And the way you can tell is because whenever somebody says, oh, I've computed 20 digits of pi. Okay, well, what they mean is they've narrowed pi down to a really small interval. So they say, I can prove that pi is between this number and this number. But they can't tell you what pi is. And if you want to prove me wrong, all you have to do is give me the first 10 to the 81 digits of pi. Right? Just write them all out, send them to me, send me an email with the first 10 to the 81 digits of pi, and you know what? I'll believe you. Anyway, so a lot of this is stolen from Wildberger's series called Wild Trig. He developed a version of trigonometry which is an improved version of trigonometry that does not use length or angle. Instead, it relies on these ideas of quadrance and spread. He also wrote a book called Divine Proportions, and so a lot of the arguments I'm going to be going through are largely just taken out of his book. It's a very good book. So, for now, given two vectors, which are, for now, just think of them as the same thing as points in two-dimensional space. There is a difference. You think of really the way to think about it is points or vectors are translations or translations of the points. So translations applied to 0, you can analogize that with points. That's maybe a way to think about it. But vectors and points are kind of distinct, but they're kind of not. Anyway, the algebraic structure is completely clear, and so what things are is kind of less important. Anyway, we're going to be working with V and W. And the normal idea is to define distance between two vectors and to define the angle between two vectors. So I wrote I kind of denoted the distance between these two and the angle between the two. And these are, this Q1 we're calling these are rulers, and Q2 we're calling these are protractors. But instead of distance, we're going to talk about quadrants, and instead of angle, we're talking about spread. Okay, so the traditional answers, there's actually a lot of answers for your rulers, and it's actually kind of interesting, especially in statistics or data science, whatever you want to call it, because there's a lot of different things that count as distance. If you want to look up what counts as distance, look up metric space. Anyway, the traditional answers are these LP norms, and so there's one for each positive integer p, and then there's one which is the limit as p goes to infinity, which is the L infinity distance, or as p gets larger and larger, it gets closer and closer to matching the infinity distance. So the L1 distance is called the Manhattan distance, and the L2 distance is called the Euclidean distance. The traditional answer that I'm going to explain here is the L2 distance, which is the Euclidean distance, but there are a bunch of these LP norms. Quadrants is none of these norms. It's maybe the L2 norm squared. That's what the quadrants is. But anyway, the traditional idea of distance, or of our rulers, is to use the Pythagorean theorem. Now, I want to note that the way that the Greeks thought about the Pythagorean theorem did not include what we now call square roots. The Greek idea was closer to quadrants, which is the idea we're talking about today. So here's the Greek idea in this diagram right here. So you take these four triangles, all of which are congruent, or that are pairwise congruent, and this empty space in the middle is of size c squared. And all you do is you move the triangle. So you move this blue triangle or this turquoise triangle from the bottom right up here, and this yellow triangle you move over here, and this dark blue triangle you move down here. And none of these transformations change the amount of empty space, but over here you have c squared units of empty space, and over here you have a squared plus b squared units of empty space. So pause the video, stare at this diagram until you're convinced that at least for a right triangle, so for a triangle where one of the angles is a right angle, that c squared is equal to a squared plus b squared. All right. So the more of a point-based idea, the modern formulation of this would be, well, you have 2 points V and W, and you want to measure the distance between them. So what you do is you build this right triangle here. So this distance down here at the bottom on the horizontal way is V1 minus W1, which is the difference in the x-coordinates. The difference in the y-coordinates is V2 minus W2 minus V2. And then, well, you go over here and you take the square root of both sides if you want to measure C. And so this blue length here would be the square root of V1 minus W1 quantity squared plus V2 minus W2. I need to clear my throat. 1 second. Plus V2 minus W2 quantity squared. And then you take the square root of that to get the distance between V and W. There's a lot of, this square root operation is very specific to the rational numbers or to the real numbers. And I don't like this, so we're not going to use this square root idea. We're going to, instead we're just not going to take the square root, and we're going to take this stuff inside and stick with that, and that's called the quadrants. So this, don't do the square root, and that's the quadrants. Sorry. I don't know what's wrong with my voice. Anyway, so the original, this is called the Pythagorean Theorem, and so this is, I botched a take earlier, so the original context in which this arrived, the Pythagoreans did not discover this. It was known long before the Pythagoreans. The Babylonians knew about it. And so I think the context in which they described it, this may or may not be true, so please don't quote me. But what they would do is they would figure out integers, triples of integers, a, b, and c, such that a squared plus b squared is equal to c squared. And what they would do is they would take a rope, and this is the most poorly drawn rope in the world. But what they would do is they would take a rope, and they would make equally spaced intervals on the rope. And so what you would do is you would take, if you want, the idea is to construct a right angle using this. So 3 plus 4, that's 7 plus 5. So you take 12 equally spaced intervals, and then if you want to construct a right angle, well, then you arrange it in this 3, 4, 5 pattern, and you're going to get a right angle. By the way, this is related to something called the side-side-side congruence theorem in traditional trigonometry, so maybe look that up. But the point is that if you have one of these Pythagorean triples, then the Pythagorean theorem goes both ways, and that's maybe a consequence of the side-side-side congruence theorem, which is that this is actually a two-directional theorem. So it's not just true that if you have a right angle in a triangle, then the triangle has the property that a squared plus b squared equals c squared. It's also true that supposing the triangle has the property that a squared plus b squared equals c squared, then the angle between a and b is a right angle. Sorry. Need to take some Mucinex or something. Okay, so this distance idea, there's a lot of different ways to denote it. So you take the square root of maybe v minus w transpose times v minus w, or it's the inner product of v minus w with v minus w, or it's the dot product of v minus w. In my notation, I'm writing this as the square root of the standard inner product of m minus, which is matrix subtraction vw, matrix subtraction vw, the standard inner product, so that's what's inside this square root, and then the square, and then, yeah, take the square root of that, and that's how you get the distance. I would have denoted this dot, but in my handwriting, dot looks like determinant, and I discovered that later when determinants come up later in this video, and but standard inner product is a better name, and one reason is because it should raise the question in your mind, what are non-standard inner products? And so I put a little bit of an answer here. So if you've done a little bit of quantum mechanics, by the way, if you've done quantum mechanics, I'm assuming you know all of this, but maybe you haven't seen the rational trigonometry, but you've certainly seen this idea. There's this notation that they use to denote the same idea. So in quantum mechanics, the answer of what is a non-standard inner product is between these two you put a matrix. So the standard inner product, the matrix in the middle here, is the identity matrix. But in a non-standard inner product you put a symmetric matrix in there. Any symmetric matrix. Or maybe it's a symmetric positive definite matrix. Properties you want the inner product to have. And so basically the definition of the inner product is this matrix in the middle. Well, in quantum mechanics, they have this wonderful notation, or it's okay notation. It's not Googleable, so that's a problem. It's called bra-ket notation. So these things like v bar angle v bar x, these are called bras, and then the other option is called a ket, and so bra-ket. And this thing in the middle is called an observable, I think. Please don't quote me on that, and please fact check me. But all this is matrix multiplication. And so in quantum mechanics, everything is with complex numbers, and so instead of a symmetric matrix, you have it's called a Hermitian matrix, I think. A conjugate symmetric matrix. That's a descriptive term. So you take the transpose of the matrix. So a matrix is symmetric if it equals its own transpose. Okay. A matrix is Hermitian or is conjugate symmetric if you take the transpose of the matrix and then take the complex conjugate of every single entry. If the matrix equals its own complex conjugate, or if it equals its own conjugate transpose, that's called a Hermitian matrix. And I believe the observables have to be Hermitian matrices in quantum mechanics. But please don't quote me, or please don't quote me on that, and please fact check me. And worst case scenario, you go and learn something about quantum mechanics. Anyway, so what I do here is just show you that these are all the same idea. So v minus w, well, you just subtract component-wise. So it's v1 minus w1 in the first component and v2 minus w2 in the second component. V minus w transpose times v minus w, well, here it is. It's v1 minus w1. This is the transpose, this row matrix here. And this column matrix is the same as up here. And when you take the product of these two, well, it'll be v1 minus w1 squared plus v2 minus w2 squared. Now, the better idea is to not even bother with the square root at all. Because the square root is this transcendental operation. It's not algebraic. It depends on geometry. I've said God doesn't care about geometry. And I should have mentioned before, right at the beginning, I said, I think in the Truth versus Reality video, I said that there's sort of a fundamental trade-off in mathematics. you can either, generally the trade-off comes in the form of you can accept some upfront complexity at first in exchange for a simpler story that makes a lot more sense down the line, or you can sort of impose some artificial simplicity up front, and in exchange you get angry dragon problems down the line. And I mean the Japanese concept of dragons, not the European concept of dragons. And I don't like angry dragons, so I'm going to accept a little bit of upfront complexity. These length and angle ideas are very visually appealing. Like, we have tape measures that measure length, we have protractors that measure angle, and they're very linear. Like, you can add two angles, and it sort of makes sense. Mathematically, it just doesn't hold up. It doesn't make as much sense. So we're going to instead accept a little bit of upfront complexity. So instead of distance, we're going to talk about quadrance, which is distance squared. Instead of angle, we're going to talk about spread, which happens to equal the sine squared of the angle, but please don't think of that as the definition. So the better idea for the rulers, we're still talking about rulers here, better idea, don't even bother with the square root and just define the quadrant. So I'm denoting it as QVW. This is just the dot product. So dot of matrix subtract VW, matrix subtract VW. This is the definition of quadrants. And so there's a few reasons that these are better. I'm not going to be able to, you're only going to be convinced that they're better by working with both systems for a long enough time. That's the way you will convince yourself that the rational system is better. However, I can sort of give you some reasons up front. If V and W have rational coordinates, and I should mention, better is relative. It's relative to your preference, and I prefer the rational system, so that's what I'm using. If V and W have rational coordinates, then the quadrance is rational. So everything here, subtraction, squaring, and addition, these are operations that are perfectly well defined over the rational numbers. Taking a square root, well, for instance, there is no fraction or a rational number. They're the same thing as fractions. They're synonyms. There is no fraction such that when you square it, you get the integer 2. And I talked about that. I gave a proof of that that's very, very simple. It's a completely understandable proof in, I believe it's WFC 2. And I will try to remember to link that. In WFC 2, let me write that down. WFC 2, which is the square root of 2, is irrational. There is no fraction such that when you square it, you get 2. So this square root idea, you can kind of narrow it down to a range. It kind of makes sense, but kind of doesn't. Instead of sort of introducing it as a primitive operation, we're just going to say, we're going to deal with quadrants instead, and that actually becomes easier. And I want to mention, real numbers are intervals, not numbers. I think I said this earlier. Real numbers are intervals. Now, what I mean by that is, if I ask you what e or pi or the square root of 2 or the natural log of 2 or any of these irrational numbers is, you can't give me a complete answer. What you can do is you can give me the first 50 digits or 10,000 digits. It doesn't matter how many digits. You can give me the first however many digits. All that is telling me, so for instance, the first 2 digits of pi are 3.1. So what that means is that pi is between, here, let me write this out. What this is saying is that 3.1 is less than pi, and pi is less than 3.2. Okay? This is not telling me what pi is. It's just saying that pi is within this interval. And this holds, so 3.14, that's saying 3.14 is less than pi is less than 3.15. All it's saying is that pi is between these two. And pretending that intervals are numbers, the mathematicians will give you some squirrely answer like Dedekind cuts or equivalence classes of Cauchy sequences. It's not for me. I understand the idea. I just don't think it actually works. And anyway, so this definition we have, which it only uses algebraic operations. So in particular, it works over a general field. Actually, this would work over a ring, as long as you have addition, subtraction, and multiplication to do squaring. So this would actually work over a ring. But for the protractors, we're going to be talking about division. So we can talk about trigonometry with z-modules, which is kind of interesting. This is going to be important down the line. Because here's a thought. I haven't actually really looked into this, but if you know a little bit about z-modules, they have this periodicity to their arithmetic. Well, therefore, wouldn't calculus with z-modules be the natural algebraic way in which to study periodic functions? So maybe you can get a better version of Fourier analysis by just doing calculus in z-modules. That's an idea. I haven't looked into that. I did buy a book called Algebraic Calculus by, I can't read the, Roderick Lumsden. I looked at it. It looks, I don't know who this guy is. It's clearly typeset in Microsoft Word, and I have a rule, which is I don't trust anyone who knows how to use Microsoft Word. So I'm a little bit suspicious of the book. But I did kind of skim through it, and it looks interesting and it looks correct. But I haven't read it thoroughly. I'm not going to have time to read it for a while. Let me write down his name, Roderick Lumsden. I better be recording. I am. Roderick Lumsden. And that's algebraic calculus. Wildberger also has a course on algebraic calculus on some stupid platform that's impossible to use. But Wildberger, I think, is kind of the guy behind algebraic calculus. I'm not actually sure. So I think this guy has the same basic orientation of Wildberger. Again, it's typeset in Microsoft Word, so you can't trust it very much. But anyway, so let's talk about protractors. So the traditional idea is angle. We're not doing that. We're talking about spread instead. The traditional idea, so you have this idea called the dot product, which we just defined above, which is, you take the transpose of the element on the left and multiply that matrix by the vector on the right. And geometrically, you can make an argument. Go look at a physics playlist. The physicists define this as the length of v times the length of w times the cosine of the angle between them. So here's the idea. Oh, I said suppose that the length of w is equal to 1, and then this gives you length of v times the cosine of theta. So that's a thought. Maybe if w and v are both length 1, then you get the traditional unit circle picture. Anyway, what you do is then, you can write out an algebraic expression for v dot w and for the length of v and the length of w. And then what you do is you say, theta therefore is equal to the arc cosine, which is the inverse function of the cosine. So the angle whose cosine is v dot w over the length of v times the length of w. What is this arc cosine function? Nobody actually knows. That this is a mystery. It's up there with who shot JFK. Nobody actually knows. Anyway, so here's the picture. Suppose that the length of w is equal to 1. Right? It looks like this. This blue length here, I don't know if you can see that, is the length of v times the cosine of theta. It's this projection idea. And so if you scale up w, then the value of the dot product scales by the length of w. All right. There's a problem here. First of all, exactly defining what an angle is actually surprisingly difficult. It requires a prior notion of arc length, which requires calculus, and so then there's a question of, okay, well, can you really trace out the dependency tree of these ideas? And also it's a transcendental notion, which means it highly depends on the geometry of Euclidean space, and I don't like that. Instead, we're going to talk about something called spread. And spread is defined as between lines, rather than between rays. So instead, what we're going to do is draw the line through the point V. So here is the origin. That's the point down here is the origin. And you draw the line through the point V, and you draw the line through the point W, and you can measure the spread between the two lines. Right? It's defined as a function on the two lines. And spread is more delicate, and it will require several videos to set up properly, and many more videos to explain why it's better. Go see Wildberger. Go read Divine Proportions. I have it here on my desk. It's a very good book. In the meantime, here is the definition. Oh, I wanted to show you this. This is a spread protractor. I have no idea if this is accurate. I just Googled spread protractor, and it kind of looks right. But, you know, come to your own conclusions. Make your own judgments. So what it is you put one line here on the horizontal axis, and then the other line will go through what its spread is. And the point is, one thing about spread is it's defined between the two lines. So it's symmetric. So if I take W with minus W, or V with minus V, or if I swap U and, or if I swap V and W, I get the same spread. And it's always between 0 and 1. So an angle is between 0 and 2 pi, never mind what pi is. And then it's maybe not single valued because, 3 pi is equal to pi in angle logic. It's very confusing. So in the meantime, coming up with the definition of this is a little bit, it's not like difficult in the sense, it's difficult in a different way. It's difficult in the sense that there's a lot of like manual labor, but it's not difficult in the sense that you can completely algorithmically write down exactly what to do. But in the meantime, here is the definition for completeness sake. Okay, let's write this as x expressions for a minute. I forgot to square the determinant, that's why this is not aligned. But so the spread between v1, v2 and w1, w2 is defined as the division, so this is a fraction, the square of the determinant of this matrix, v2 minus v1 minus w2 and w1, divided by the product of the quadrants of v and the quadrants of w. Close the times, close the division. So here, close the determinant, close the square. And in normal notation, this is w1 v2 minus w2 v1 quantity squared over v1 squared plus v2 squared times w1 squared plus w2 squared. Notice that this is symmetric in two ways. So if I swap v and w, this quantity up here doesn't change. So try that. So replace v1 with w1 and v2 with w2, and vice versa, and make sure that this is the same. You can also replace v with minus v. So what would happen here is you would switch the sign of v2 and switch the sign of v1, but since there's a minus sign here, the quantity in here gets negated, but it also gets squared, so it doesn't matter that you negate it. And then you're squaring it here, so it doesn't matter. Same with the w, same thing happens. No change to outcome. And like I said, you can swap the rules of v and w with no change to the outcome. So that's an outline of what we're going to be talking about the next few videos, is rational trigonometry and this better idea of how you do basic geometry in the plane. And in particular, geometry is largely based on triangles, and triangles traditionally are based on notions of length and angle, and that's sort of assumed throughout mathematics that that's the correct way to do geometry. Maybe it is, maybe it isn't, but this quadrants and spread idea, this rational trigonometry idea, I don't know if it reduces the angry dragon problems. It keeps the angry dragons away, and that, and if for no other reason, it's interesting. It's interesting that you can do this. Anyway, that's all I wanted to talk about for now. I'm not sure actually what I'm going to talk about in the next video. Probably explain how this, where this spread definition comes from. Anyway, maybe if you want to peek ahead, go look at Wildberger's Wild Trig series, or go buy a copy of Divine Proportions. Anyway, this is related. I said I wanted to talk about the inner products perspective on linear algebra and talk about a few things before we move on in Artin. I think we're ready to move on, but I do want to... There's some more things I want to talk about while I still have the steam in my head, but probably we're ready to move on in Artin. I'm not sure yet. Anyway, that's all I want to talk about. Thank you for watching. I will see you in the next video. Bye!